project for the Presidential AI Challenge. Data centers are growing quickly, and cooling is one of the largest sources of electricity use. Facilities typically decide when to use outside air cooling based on fixed temperature and dew point thresholds such as ASHRAE guidelines. These rules are designed to be safe, but they are static and often conservative, which can prevent data centers from using energy-saving cooling strategies even when conditions may allow it. The objective of my project is to test whether AI models can predict high-efficiency cooling windows more effectively than traditional rule-based methods, and whether those predictions can identify additional safe opportunities for reducing mechanical cooling and energy use. I use three datasets. The first is high resolution operational telemetry from the Oak Ridge National Laboratory Frontier Supercomputing Facility. This dataset includes compute power, total facility power, waste heat, and detailed cooling system variables such as coolant supply and return temperatures and flow. The data is originally at approximately 10-minute resolution and is aggregated to hourly intervals when combined with weather data. The second dataset is NOAA hourly weather data for Oak Ridge. Weather is important because outdoor temperature affects cooling demand, and dew point is a stable measure of moisture and condensation rates, which is why it appears in many cooling guidelines. The third dataset is a multi-site Virginia dataset center with a lower resolution but broader coverage. It includes variables like facility size, location, and power capacity. This dataset is used to test whether patterns learned from a single high-resolution site can generalize across a fleet of data centers. My research questions ask, how cooling system variables relate to total power use, whether AI can predict high efficiency operation periods, whether adding weather improves these predictions, whether insights generalize to other sites, and how much energy and carbon emissions can be avoided during predicted efficient cooling windows. To answer these questions, I start with feature engineering grounded in the physics of cooling. I create temperature deltas, flow normalized metrics, and cooling overhead ratios that represent how much energy is used beyond compute power. I then define high efficiency operation as the lowest 25% of cooling overhead, which corresponds to only about 4.5% of total power being used for non-compute overhead during the most efficient hours. I then train multiple models, including baselines like linear and logistic regression, and more flexible nonlinear models such as random forest and gradient boosting. The models are trained to predict whether the next hour will be a high efficiency cooling window. I also build a rule-based baseline inspired by ASHRAE temperature and dew point thresholds so that AI can be directly compared to traditional decision rules. The results show that combining operational telemetry with weather data improves predictive performance. Among all models tested, the random forest model performs the best, achieving a ROC-AUC score of above 0.93 when predicting next hour efficiency, indicating strong separate between high and low efficiency periods. On the graphic, it shows 0.76 without these ASHRAE guidelines, and then once added to it, it comes up to this 0.93. When comparing AI predictions to ASHRAE style rules, the differences are especially important. About 43% of hours are flagged as eligible by rules but predicted by the AI to be inefficient, suggesting rules can be overly permissive without considering system behavior. At the same time, about 4% of hours are flagged as efficient by the AI but blocked by static rules, highlighting potential missed opportunities for safe efficiency gains. This shows that AI can capture interactions among weather, workload, and cooling dynamics that static thresholds cannot. To make the solution practical, I implement the model in a Streamlit application. The app takes current conditions as inputs and predicts whether the next hour is likely to be a high efficiency hour cooling window along with estimated energy and carbon savings. This demonstrates a functional decision support tool rather than just an offline analysis. Finally, I explore generalization using the Virginia dataset by mapping learned efficiency drivers to proxy features such as power density across many sites. While limited by lower resolution, this analysis shows that the approach could scale to real-world data center fleets. In conclusion, this project demonstrates that AI-based decision support can improve cooling efficiency, reduce energy use, and lower emissions while respecting safety constraints. It provides a framework that combines physics, machine learning, and real operational data to support more sustainable data center operations.